We are now going to shift our focus in the course towards area calculations. Specifically, one of the mathematical problems that's been of most interest since the ancient Greeks was how do you find the area of a curvy region? And you can see the applications of that almost everywhere. In fact, here's one right in front of us here. The area of the state of Texas, right? Texas is obviously not a nice geometric region that you can just use formulas for. It's got lots of curves and borders. And so a big question came about, well, how do you find, or at least approximate accurately, what the area of Texas would be? And there's lots of ways you can go about doing these approximations, and we're going to learn 4 of those techniques today. They're called Riemann sums, after this guy whose picture is shown here, German mathematician, and this is how we spell his name, R-I-E-M-A-N-N. Okay, Riemann sums. And those are using geometric figures to approximate the area of a curved region. Now, what geometric figures can we use? Well, we can use any ones we know formulas for. And the most common ones are rectangles, circles or portions of circles, and trapezoids. So, there's going to be 4 that we talk about today. And I'm not going to read every one of them word for word. You should pause the video and make sure you understand what's being done in each one. But I'll read the first one for you. We're going to do a left Riemann sum first. What do we do to do a left Riemann sum? We divide our region into subintervals. They don't have to be equal, but today in this video they will be. And use the function value of the left endpoint of each subinterval to determine the height of a rectangle. So that'll become obvious as we start to go through this, what's actually happening here. So this is a picture of the curve 1 over x on the interval 1 to 2, as you can see down here. And so we'd like to get an approximation for what this area is. Okay, this region is not a geometric figure, it's got a curved boundary, so we can't just use normal geometry. Alright, for today's purposes, we're going to use 4 rectangles, or 4 trapezoids. The problem generally will specify what they want you to do, and we'll use equal subintervals. So the first thing I need to do is take my interval from 1 to 2 and divide it into 4 equal pieces. Okay, the graph here has conveniently done that for me. So 1 to 1.25 is one subinterval, 1.25 to 1.5, 1.5 to 1.75, and 1.75 to 2. So I have 4 subintervals. Now, each subinterval is going to determine a rectangle. And the only question is, since I know the width of the rectangle, how do I do the height? And the type of Riemann sum tells us. So if we're doing a left Riemann sum, we use the left endpoint of each subinterval to determine the height. So in subinterval 1, left endpoint is x equals 1. And so we'll use the y value when x equals 1 to determine the height. So this point up here determines the height of the first rectangle. And I'll go ahead and draw that first rectangle so you can see what I'm doing. So there's the height. The width is 1.25 as was determined by the number of subintervals and the fact that we're using equal subintervals. Okay, so now let's go ahead and fill in the rest of the points that will determine heights. So if we're using the left endpoint to the second interval, that's x equals 1.25. We use the y value on the curve. And in the next subinterval, we use 1.5, the y value that's on the curve, and 1.75. And let's go ahead and draw in the rectangles. Okay, so now we have 4 rectangles that I can calculate the areas of, and that'll give me the approximation for the area of the region between the graph of f and the x-axis between x equals 1 and x equals 2. Now, you should note, obviously, that this is going to be an over approximation because there's portions of these rectangles that lie above the curve. So whatever answer we get, we will understand that it's going to be slightly over the real area, but all we're after here is an approximation. Okay, so I'm going to go ahead and type in the areas of these 4 rectangles. So the first rectangle has a width of 0.25, and the height is going to be the y value on the curve when x is 1, so we would call that f of 1. The second rectangle has a width of 0.25 and has a y value f of 1.25. The third rectangle has a width of 0.25 and a y value of f of 1.5. And the last one, width is the same, And the y value is f of 1.75, which we could calculate because we know what f is. And we could obviously evaluate that by hand in this case, but I've gone ahead and done that to save time with the calculator. And here's what we would get for our area approximation. Okay, we would get 0.759, etc. And we understand based on our picture that this is going to be a little bit more than the real area. Pause the video, take a look at what a right Riemann sum is, and then let's jump ahead to the picture. So the differences between a right and a left are just that you use the right endpoint of each of the subintervals instead of the left. So in this case, f of 1 does not get used as a height, and instead f of 2 gets used. So those 4 dots determine the heights of the rectangles. Let's go ahead and draw those rectangles in. Okay, in this case, we can see from the picture that the area of these 4 rectangles will be slightly less than the true area because there's all this extra space under the curve that's not being accounted for with the area of the rectangles. Okay, now let's go ahead and type out what these areas will be. So the first rectangle has a width of 0.25 and a height of f of 1.25. Second rectangle has the same width. Height is f of 1.5. Same width for the third rectangle. F of 1.75 is the height, and same width, f of 2 is the height of this one. Okay, and again, we could do that by hand if we had to. Calculators are obviously helpful here, and I've gone ahead and taken care of the calculation. So now we get 0.63, 452, etc. And this is going to be an under approximation to the true area. So far we're somewhere between 0.63 and 0.75. So we have kind of a bound for where the area really is. Pause the video and understand what a midpoint Riemann sum is. Now instead of using left or right endpoints, we're going to go in between the left and right endpoints and use the midpoint. So what is the midpoint between 1 and 1.25? Well, you add these two numbers together and you divide by 2. That's how you get the midpoint, and we'll do that calculation in a second. But the dot goes halfway in between, and you just go up to the curve and find the y value that corresponds to that x value. Okay, so I'm going to do that for each of the intervals, subintervals. And now let's go ahead and draw the rectangles. You're going to be tempted when you do some of these problems not to draw the rectangles, but I'm going to encourage you to do that because it's so helpful seeing what you're actually doing with the geometry. And you will be less likely to make mistakes as far as where my function values are coming from. Okay, so there I have 4 rectangles. It's now not obvious whether this is going to be more or less than the true area, because now I have some area above the curve or some area below the curve that's not accounted for, and then some extra area above the curve that the rectangles produce. So I don't know whether this would be more or less than the real area, but it's going to be a little bit more accurate, I would say, than the other two. Okay, so once again, 0.25 are the widths, and now if I calculated the midpoint between 1 and 1.25, I would get this number based on the midpoint formula. The second rectangle would have a y value of f of 1.375. The third rectangle, 1.625 is the x value, so the height is f of that number. And the last one will be f of 1.875. And let's go ahead and take a look at what the calculator says that number is close to. With a function like 1 over x, it's not hard to do this by hand, but 0.6912, etc. So this is closer to the real answer. I can't tell for sure whether this is over or under. Okay, the last one we're going to look at is a trapezoidal sum. And so this one's a little bit different because we're not using rectangles. And read what that is, and then we'll show you on the picture. So with the trapezoidal sum, we actually take both endpoints of each subinterval and put the dots on the curve, and then we're actually going to connect those dots with a line, and that's going to create a trapezoid. And we'll have to talk about area of trapezoid in a second, I think. So I've created all the endpoints on the curve, and now if we go and connect those dots with lines, we create 4 trapezoids. And the good thing about the trapezoidal method is, in general, it's the best one because trapezoids hug the curve the best. So 4 trapezoids are created here. The trapezoids are, I would say, horizontal trapezoids. In other words, the height is actually this distance here, whereas normally when we draw trapezoids, the height is vertical. So let's review real quick. What is the area of a trapezoid? Okay, the area of a trapezoid is going to be 1/2 the height, which is really the altitude. It's a line segment that goes between the two sides that's perpendicular to the two sides. So our heights are going to be these distances down here, the widths of the rectangles that they used to be. Okay, and then we say base 1 plus base 2. Okay, now what are the bases? Well, in this case, the bases are the two sides of the trapezoid that go vertical. So it's going to be a little bit different than maybe you were presented with in geometry class, but same principles apply. Okay, so my approximation is going to be the first trapezoid will have 1/2 is in the formula. The height of each of these trapezoids is 1/4, 1 to 1.25. Okay, and now I'm going to add in parentheses the two bases. So f of 1 is the first base, and f of 1.25 is the second base. That's the first trapezoid's area. Okay, we now move on to the second one. The first part stays the same. And now the two bases are f of 1.25 and f of 1.5. Third trapezoid, first two parts stay the same. And now we're going to use f of 1.5 plus f of 1.75. We move that out of the way. And then the last trapezoid will be 1/2 times 1/4 times f of 1.75 plus f of 2. That's what I would try to do by hand if I could, or what I would enter into the calculator. And so here's what the calculator would give us for this function. Okay, 0.69702, etc. And how does that compare with the one before? 0.691, and this one says 0.697. Now, if we're very careful, we can tell whether this is going to be more or less than the real area, because I can tell that these are secant lines, right? These line segments that connect the endpoints on the curve. And if my curve is concave up, as this curve is, then I know secant lines lie above the curve because the tangent lines lie below. So there's actually extra area above the curve that's being created by the trapezoids, and so this is a little bit more than the real answer.